to lecture 12 about the nested fixed point algorithm, or shortly NFXP. So NFXP is used to estimate dynamic structural models in general. And we'll focus here on a very specific class of structural models, namely dynamic discrete choice models with a single agent. So this was first applied in Rust 1987, published in Econometrica, that has this very cool title, Optimal Replacement of GMZ Bus Engines, an empirical model of Zurcher. And that's really what it is. It's an empirical model of the superintendent of maintenance, Zurcher, who comes into his workshop and checks out the buses and figure out if you want to replace the engines or not, thinking about how that affects the future cost of maintenance and operating the buses, and thinking about how much time it costs to replace the engine. So it's really one of those renewal problems. It's like, the Clash would say, should I stay or should I go? Okay, so we'll look at that. Okay, now just to give a little bit of the overview of Rust 1987. This is really a path-breaking paper. It's the paper that introduces the new methodology to estimate single-agent dynamic discrete choice models. Here it's with maximal likelihood, but the approach is actually quite general. You can use it within other estimation frameworks such as GMM or nonlinear least squares or quantile regressions, whatnot. It's as long as there's some sample criterion based in estimation that that includes some fixed point that needs to be solved. Well, we can kind of call it the nested fixed point algorithm, because there's a nested fixed point embedded inside an algorithm that search for parameters in order to fit the model to the data. Okay, and that's the idea. So we're going to go much more into detail with NFXP, and here we do it in the context of maximal likelihood. So you'll see all the equations. The main contributions of this paper is, first of all, it gives this very illustrative application of a model, or a very simple model of engine replacement. And this was what was feasible at the time in 1987. You had to work on a supercomputer to solve this, okay? And in fact, when John Rust first submitted this paper to Econometrica, the editor, Angus Deaton, actually says, this sounds pretty good, but I want to see that this is actually possible in reality. Show me an example. And then he went out and met Zurcher and got rid of his, got to his data and got his hands dirty. As John would say, he literally got his hands dirty because it was like grease all over the books where he has written down what the mileage was when the bus engine was replaced and so on. Okay, so that's like the first contribution, this nice application in a simple renewal problem. And this is a very, it's actually a very broad class of models if you think about it broadly, replacements of assets, right? So that's in itself is a contribution. And then he has this development and implementation of the nested fixed point algorithm, as we'll go into details about. One of the things that actually makes this paper very important is that he formulates a set of assumptions that make dynamic discrete choice models tractable. I'm going to talk about those assumptions in detail, what they bias us in terms of reduction of computational complexity, and what they mean in terms of the restrictions they put on the data. One of the things that you would assume is, for instance, that the errors are at extreme values, so you get logit formulas for the choice probabilities. One of the things you would assume is conditional independence on the error terms in the model, conditional on the state variables. But you'll see that. So he's the first researcher really to obtain maximum likelihood estimates of discrete choice dynamic programming models. Beyond that, he develops something he calls the bottom-up approach for obtaining microaggregated demand for durable assets. Okay, in this case, a durable asset is a bus engine, but this applies much more broadly, to airplanes, machines, and so on, right? Cars are there durable assets that you buy and replace once in a while. And so by using the model, solving it, and then you can simulate what the equilibrium distribution of this asset would be, or the equilibrium demand would be, and then vary what the replacement cost would be, and then that's the price of the asset, right? The replacement cost, and you got a demand curve implied by the structural model. So this is entirely new at that time. He runs a bunch of policy experiments and considers really what does the change in replacement cost affect the distributional mile routine and then the demand of engines. Okay, so you may ask, who cares about Harold Zurcher? I mean, this is a Mickey Mouse sized problem, one state variable, one binary choice, and why are we spending time on a 30-year-old paper? Well, like I said, it was really path-breaking, and I've already listed some of the contributions, and in many dimensions, this paper was really ahead of its time. Several years after the paper came out in econometric, it only cited a couple of times, like 7 times for a couple of years after the paper came out. And now it has more than 2,000 sites, and people are starting to use dynamic structural models much more frequently throughout the literature. And this paper really started that wave. So here's a bunch of references to papers that essentially relies on the framework, or at least versions of the framework that John thought about at that time. So one example is occupational choice. This is a discrete choice, right? Should I go to school and watch online lectures, or should I go out and get a white-collar job or a blue-collar job, or should I go to the military or just stay at home? And that's actually the discrete choices that you make, that the agents make in the model, in the paper by Keene and Volpin, Career Decision of Young Men in JPE 1997. Here, the decisions has implications for your future accumulation of human capital and therefore also your earnings and so on. So you make the trade-off, should I go to school now and earn more later, or should I just go out and get a job? That's a discrete choice model estimated on microdata. This is what we're going to do today. Okay, retirement is another example. John Rust and Chris Phelan had a paper in Econometric in '97 that deals with that and implements the whole institutional framework in retirement benefits and so on inside this model. Again, a binary choice, and then there's more bells and whistles in terms of institutional framework and so on. Brand choice and advertising, right? I mean, you choose between Coca-Cola and Pepsi and cereal and vegetables and a bunch of stuff. You go to the supermarket, and then once you start thinking about advertising from the first point of view, well, they may want to think about that the consumers are forward-looking. So you put something on sale, they go out and buy a bunch of stuff, and then they're not going to buy it at a lower price next period. That's a dynamic discrete choice problem that consumers are facing, and the firms may want to take that into account. So here's a whole list of papers that you can look at the references, but you can see where I'm going. This is a super general approach, and therefore we're also going to talk about the general behavioral framework in just a minute. Okay, so I'm going to divide this lecture into two. And first we're going to focus on Zurcher's bus engine replacement problem and then the general behavioral framework that it fits into. In particular, we're going to discuss Rust's assumptions and the implications of them in terms of what it puts of restrictions on behavior implied by the model, but also what it biases in terms of the reduction in computational complexity. And then next, we're going to talk about, and you can say this is about how you solve the model. Next, we're going to talk about how you estimate the model and go into detail with the nested fixed point algorithm and present the empirical results. Okay, so just to, a little bit of a reminder of what is involved in formulating, solving, and estimating a dynamic model. Well, let's first start thinking about what are the components of a dynamic model? Well, this decisions variables. Okay, decision variables affects the evolution of the state variables, and so we call the decision variables D. And these decision variables in discrete choice models is a finite set of outcomes, right? They are mutually exclusive. Then the choice set C can actually depend on the state variables. Like, for instance, you think of a life cycle model, or where at some point you don't have the decision to get children anymore because it's just not possible. So it will get out the choice set, right? As you age, for instance. Okay, so this could be state dependent. Okay? Or you make a decision like a permanent contraceptive choice that makes it impossible to get children, and then that state, if you have that permanent contraceptive choice, then makes it impossible to choose the option of trying to get a child. Cool. So choice sets can be state dependent. It's not here. In Zurcher's model, it's really just a binary indicator, 0 and 1. He can always replace an engine if possible. State variables. The state variables, well, that's the state. That's a variable that describe all relevant information about the model decision process. Okay, so it doesn't. In order to predict what the future discounted utility is, well, you don't need to know anything else about these variables. Okay, it may be that other variables affecting your future utility, but there's no information. All the information that you have to make expectations about how those variables develop must be contained inside S. Then there is a utility function, U. Okay, so we'll call that U. Okay, so here this is a function of the state variables and decision variables. You get different utility in different states, and it may also be that utility is affected by your choice. Like in the example here of Zurcher, he'll have to pay the replacement cost of replacing the engine if he chooses to do so. So it's highly state dependent or choice dependent. Okay, and then there's the motion rules or the transition rules of the state variables that captures the agent's beliefs on how the state variables evolve through time, conditional on the states and decisions. So these are controlled macro processes. Okay, they're controlled in the sense that they depend on the decision variables, and they're macro processes in the sense that we only consider the next period, the evolution between two successive periods of states. Well, is that really a restriction? It's that we're looking at a first order macro process? Not really, because if there was a second order macro process, well, then you'll start to include more state variables like the lags of the state variables that you have to begin with. Anyway, so we formalize this by this macro transition density that we call P as given S t plus 1 given S t and D. I mean this one here. Okay, so that's the components of the model largely, and of course you can put all sorts of bells and whistles on this model and have many state variables, many decision variables, and so on. So the solutions to these models, well, they are given by the value functions, the maximal attainable utility at each state, or discounted expected utility. And the policy function that gives a mapping from the state space to the action space and returns the optimal choice. So how do you find those? Well, you use dynamic programming, right? And we've already covered that in previous parts of the course, how you can solve these models by, say, successive approximations. If it's a finite horizon model, like with the value function iterations, it's just going on and on, or with policy iterations, or by backward induction if you have a finite horizon model. So we don't only want to solve the model, we want to estimate the structural parameters, right? Because we don't know where the parameters are. Fortunately, we have data. We have microdata, for instance, and then we can build the likelihood function based on the model that we maximize in order to make, so to say, the predictions for the model fit the data. Okay. This is what we're going to talk about in the second part. So that involves parameterizing the utility function, for instance, and you may have some parameters that index that. You want to parameterize the transition rules or the motion rules for the state variables P, and perhaps even the choice sets. Okay, like if you have a parameter that's indexing liquidity constraints and you have a continuous choice model, you can put it in there. And so this is, once you have a parameterized model, well, then structural estimation is really about searching for these hopefully policy invariant parameters or structural parameters so that the model fits the targeted aspects of the data, in a broad sense. And this could be like the distribution of the joint distribution of replacement and mileage, or it could be only features of the data. If you want to do like method of moments, method of simulated moments, you only look like a specific features of the data. There are sufficient statistics to identify the structural parameters of the model. So we're going to do maximal likelihood, and you'll see all the equations. Okay, so let's go to the engine replacement model of Zurcher. So the binary the choice set C is binary, 0 and 1, 1 for replacement, and so each bus comes in for repair once a month, and then Zurcher, he looks at it and decides whether he should just do ordinary maintenance or do a complete overhaul of the engine and or an engine replacement. So Zurcher says that if you make a complete overhaul of the engine, it practically becomes as good as new. So Rust is looking at these two binary outcomes. Then the state variables, S, is partitioned into two separate variables, X and epsilon. And X is the mileage since last replacement of engine replacement. This is when we go and try to estimate this model, this is what we have data on. This is an observed state variable. Now, what will be very important later is this distinction between what is observed and what is not observed. And epsilon, that is what we'll call an unobserved state variable. Okay, so it's unobserved to us as researchers, but Zurcher, he observed it when he makes a decision. It's a decision-specific state, so there is a shock or a value of the state if you choose to keep the engine or if you choose to replace the engine. Very much like you've seen in your econometrics classes when you went through the logit model, there is taste shocks there, right? In the radar utility model. This is where we had. Okay. Then the utility function here is additively separable, and this is one of Rust's assumptions, and that buys you some simplicity. So it's additively separable in the sense that the part of utility that has to do with the observed state variables X, or mileage, and the decision to replace or not is separable from the other state variables. So these other state variables, these choice-specific phase shifters, epsilon is really just shifting up and down the payoffs of replacing an engine. So you can think of these as, what can we think of them? You can think of them as like idiosyncratic shocks to investments. Sometimes the bus just comes into repair, and it just looks, super good. There's nothing to repair, and it's not just it's not captured by the mileage of the bus. It's an old bus, but it's just looking so good. Everybody knows this is like the good bus. Or sometimes there's there's missing parts, or it's just there's no staff to replace the engine, or maybe there could be a shock to the investment cost. Maybe it comes in for repairs and it's just too super expensive to do it this week. Or it comes in and it's smoke all over the place and you have to replace it even though it's brand new. So these are like phase shifters or idiosyncratic shocks to the replacement decisions that are not captured by the age of the bus or the mileage of the bus. Okay. Now, so if you replace the bus, you would need to have, sorry about that. You need to replace the engine, so you need to pay the replacement cost, RC. If you do not replace the engine, well, you don't have to pay RC, so it's not appearing down here. What you do have to pay is the operating and maintenance cost, C, which is increasing in the age of the bus. And everybody who owns an old car knows what I'm talking about. It's getting older and older, and it's just going to the workshop all the time. All these things are it's falling apart. Okay, so it's natural to model the cost function as some increasing schedule of as a function of mileage. This is what this is capturing. Now, if you replace the bus, right, then you don't have to pay replacement cost, the operating cost, or at least you pay the operating cost of a brand new bus where X is equal to 0. So this is a utility, and this is how you see utility suddenly becomes decision dependent, because if you choose to replace, well, then you have to pay replacement cost and lower maintenance cost. But if you keep on going, well, you have to pay the maintenance cost of whatever aged engine that you have. Now let's move on to the state variable process, because this is what makes the model dynamic, right? You make a decision today that has effect on how the state variables tomorrow is going to be. Okay, so you replace the engine. Well, the engine is going to be new next period, and this is exactly what is captured by the state variable process here, and this is what Rust called a regenerative random walk, in the sense that if the engine is replaced, the state of the bus just regenerates to 0. You can see that here, you put in a 0 instead of X. Okay, so this is the motion rule that determines how the bus mileage is evolving over time as a function of the mileage today and as a function of whether you replace the engine or not. Now, we want to estimate this model, right? I mean, in order to be able to use the model to run counterfactuals and see how the demand changes as you change the replacement cost, or to figure out what the accumulated discounted cost of in operating a bus is, stuff like that, and to figure out what the optimal replacement is, well, you need to estimate the structural parameters, okay? Because we don't really know what the replacement costs are, and we don't know what the cost function parameters are. So the cost function parameters theta1 and RC are the parameters we want to estimate. Then also the parameters that indexes the development of the state variables, theta3 that enters in here, is also parameters we can learn about from data on replacement and mileage. In fact, you can estimate that non-parametrically. You don't even need the structural model. We're going to fix some of the parameters. Well, I haven't showed you the parameter beta, but I guess everybody who's seen a dynamic model can pretty much get what it is. It's the discount factor, and it's on the next slide. And then theta 2, well, that's the parameters that indexes the state variable process for the unobserved state variables epsilon, and is entering in here. Now, we can, as is conventional in discrete choice models, you need to make normalizations. You need to make a scale normalization because the variance of the error term is really not identified. And you need to make a level normalization. Okay. Now, for the scale normalization, we need to fix the scale of that distribution. And so we're going to work with the extreme value distributed errors, and it doesn't have any parameters. It's just, it's a function without parameters. Okay. So when there's no parameters to estimate, you can put in parameters, but then we'll have to normalize it to 1. If you wanted, you could actually if that's okay, you could let the epsilon be the distribution of epsilon be a function of the states. Say you want to have like higher variance of epsilons when buses they get older, and that's actually feasible within the framework, and then there would be a parameter to estimate. We're not focusing on that. Well, we're not going to do it because it's not in the paper. Okay, so now to the dynamic formulation. Okay. Now that was the core parts of the engine replacement problem. We're going to now talk a little bit more general, and then we'll turn to the engine replacement problem later. But what Harold Zurcher is doing here is that the decision maker, in this case Harold Zurcher, he's choosing the sequence of actions to maximize the expected discounted utility over some horizon. Okay, and Harold Zurcher's horizon is infinite, but this idea also applies to fine horizon models. In that case, we just have to index the value functions and the choice probabilities with the index of time, and solve the model by backward induction instead of finding a fixed point. Okay, so here, what do we have here? We have that the value function here, as a function of state variables, is the maximum expected discounted utility from now on and into the future. Okay, and it's a maximum with respect to the optimal replacements or the optimal discrete choices that we call D. Okay, so phi here is just the sequence of all those policy functions. Beta is the discount factor, U is the utility function, and we may consider infinite horizon, which is actually what we're going to do in the case of Harold Zurcher. And then expectations here summarizes the expectation of the future states, conditional on the current states S and the decisions, okay, which is why the whole thing is being dynamic. Now this is the value function. The problem Harold Zurcher is solving is through finding those policy functions pi that maximizes that future stream utility. And as you all know from your previous part of the course, by the Bellman's principle of optimality, then this value function can be calculated recursively by formulating a Bellman equation and then successively, if you want to solve it successively from the last period and on until the period of consideration, you just successively approximate or successively put into the Bellman equation. So let's just take a little bit of a look at this Bellman equation. Now, a few things first. In case of the Harold Zurcher problem, there's two state variables, x and epsilon. Okay, so now we're back to Harold Zurcher. Actually, the state variables here, the state variables are both x and epsilon. Okay. Now, what you do is, in order to calculate the value, well, then you need to know what the value or the future value is. So we need to solve this fixed point problem with v on both sides. We know what the utility function is. Usually you just have that in closed form. And we may also use how to solve that expectation operator, but we'll have to do it. This expectation is taken over the next period values of the states S prime, and here I denote prime to just note the future value of the state. Right? We drop time indices because we are looking at an infinite horizon model where the solution is stationary. Okay, so these expectations are of next period state X prime epsilon prime is calculated given the control motion rule P, the state variable process. Okay, and this here requires a double integral from over the state variables X and over the epsilons here. Okay, so this is the support of the epsilons, if you will, which is essentially r to the power of j. Okay. So, because it's going to be an epsilon for each discrete choice. Okay. So this can actually be pretty hard to evaluate just the Bellman operator. Okay. X is continuous and epsilon is continuous, and if you have many discrete choices, that is really nasty because then you have j additional continuous state variables, okay? And you all know about the curse of dimensionality, that the computational complexity is increasing exponentially in the number of state variables. So just think about if you had like just 10 points of support for that continuous unobserved state variable for each of the j dimensions, it would be like 10 to the power of j. So you see where I'm getting. If you have like one state variable is 10, it's 100. If you have if you have 2, and then you multiply it by 10, so it's 1,000 and so on. Yeah. It's just going like crazy. Okay. So exponentially increasing cost of computation. Okay, and this is the dimensionality of V, right? So this is the big object, and if you want to solve the fixed point problem, well, then you're looking for a very big solution. But that's not the only thing. The only problem is it's not only a problem that V is high dimensional itself. It's also a problem that we need to calculate this high dimensional integration over these j dimensional integrals. So just the fact of evaluating it requires some heavy duty simulation or lots of quadrature points but you also need to be able to evaluate it at the values x prime and epsilon primes that are not necessarily on the grid that you have for x. So you need to do a high dimensional interpolation or approximation of the value function. Okay, so the bottom line is this is actually potentially really, really difficult. Okay, and finally, then, because we have a discrete choice problem, actually the value function is non-differentiable. It's a bunch of overlapping choice-specific value functions that you take the max off. So you got the upper envelope of that has a bunch of kinks in each of the points where you go from, say, replacing or not, or where you go from one discrete choice to another. So that has some severe implications when you want to do structural estimation, because now all of a sudden you get all these numerical difficulties when trying to maximize likelihood function that depends on non-differentiable objects. Okay, you can't use gradient-based solvers and so on. So yeah, pretty nasty. Okay, so then it's good that we have read this paper, right? Because Rust 987 actually outlines the solution to all these potential problems. The first one, the first, the first assumption that he's making, and it's called additive separability, and you have conditional independence and extreme value type 1 errors. I'm first going to talk about the implications of the assumptions and meaning of the assumptions, and then about all the computational benefits that it buys us. Okay? And of course, you can deviate from some of these assumptions, or you can make the model more flexible in other cases, in other places that make these assumptions matter less. Like the first one here, the additivity assumption, saying that the epsilons, the unobserved state variables, are additively separable in the utility function. What it does is that it allows us to separate out actually the deterministic part of the value function, which is really, really good, as you'll see. It has some implications, like, for instance, the model we will look at in a few lectures from now about the occupational choice for young men, the career decision of young men. Here, some of the epsilon shocks are actually not additively separable, and we'll discuss how to deal with that. And this is also why, well, Keen and Volpin, who wrote that paper, is relaxing that assumption and using a slightly different version of the algorithm. Then, so it's an assumption that is not always satisfied. Sometimes the epsilons could be inside the utility function here, or they could be multiplied to the utility function. Okay. That's not too bad. Then there is the conditional independence assumption. Okay. Now here the conditional, what the conditional independence assumption says is that the state variables S that factors into X and epsilon obeys a conditional independent macro process with this probability density. I mean, this is just reading out from the paper. But what you should notice here is, well, we can separate this joint density into two that are conditionally independent. And the first one has to do with the epsilons, the distribution of the epsilons, and it doesn't note what it doesn't depend on. It doesn't depend on the epsilons today. It doesn't, once you have conditioned on the same period value of X, there's no further dependence on epsilon. Okay? So you can say that's conditionally independent. And it's really a noise that's superimposed on the problem. Okay? Now you can allow them to be correlated jointly within a period, but it cannot depend on X, on X, other than the way xt affects xt plus 1, and thereby affects xt epsilon t plus 1. Okay? Maybe you lost it, but conditional independence, well, it rules out some patterns, for instance, for epsilons. Epsilons cannot be serially correlated, right? Because there's nowhere here where epsilon is entering. Epsilon t has no effect on epsilon t plus 1, so you can rule out serial correlation. Okay, so let's think about, is that an issue for Harold Zurcher? Well, if you cannot capture everything in the mileage of the bus as description of the state of the bus, then it'll be an epsilon, right? And then think about if there's several types of different buses, okay, like heterogeneous, expensive buses and cheap buses. Okay, then and if you do not account for that in X, then it's going to be an epsilon. So epsilon's going to have a persistent fixed effect component, which is persistent, and it's just ruling out. It's just not obeying the state variable process, not obeying this conditional independence anymore. But is that really an issue? Well, you can just put in an additional state or an additional type and model that explicitly, but you would have to model it explicitly. and not relegated to the error term. You cannot have like a real serial correlation where you know the value of epsilon today has a causal effect in the value of epsilon tomorrow. So what is a good example? I mean, maybe you could think about that. What a good example would be. So on the top of my head, I'm thinking there's maybe some too much congestion at the workshop, and so therefore there's a negative shock to investment that week. It's just queuing up a bunch of buses, and Zuercher is busy replacing other buses. Now, it's likely that the day after he's not going to be done, and therefore those epsilons are going to be serially correlated. Okay, so these are just examples. And, you know, you really, when you build models, need to put in meaning to the assumptions that you're making, and trying to think what they actually mean, and can you live with those assumptions, because you have to cut corners. It's really like, you know, they say in the fairy tales, it's chop a heel and cut a toe. Okay, so moving on to the third assumption, the extreme value type 1 assumption. So it's if you assume that the errors, the epsilons are at extreme value, distributed and independent, like we'll do here, assuming that the epsilons has this you know, extreme value type 1 distribution with this cumulative density, then it automatically obeys the conditional independence assumption. So 3 is actually implying 2, or EV is implying CR. What is this buying us? Well, you know, it's giving us logit choice probabilities. It's giving us closed form for the expected value of the max. So you'll see. Okay, so let's see how that simplifies the problem. So here is what we're trying to solve. Okay, I've already used the additivity assumption, and I've also already so put the epsilon outside the utility function, and I also pasted in the conditional implications of the conditional independence assumption, which is here. Now you got this state variable process is factoring in these two in this way. Interchange the order, but compared to the last slide. What does it give us? Well, what it gives us is it allows us to separate out the deterministic part of the choice-specific value function. Okay, I've not defined this. I'm going to do it on the next slide, but you can really see it here, right? What is only dependent on the value is only dependent on the observed state x and the discrete decision. Well, utility, the utility. And we want to have deterministic parts, so not this guy here, but then we have this whole part here that is inside here only depends on x. Okay, so and actually you can integrate out those epsilons, and then the whole thing only really just depends on x and d, the variables we condition on in these transition densities. Okay, you can also reformulate the Bellman equation on a reduced state space. For example, the expected value functions instead of the value functions, or in terms of the integrated value functions instead of just the value functions. I have 2 slides with that, so don't freak out if you don't know what I'm talking about. And then you can get the expectation of the maximum and choice probabilities in closed form if you use the extreme value distribution. So this means you don't have to calculate this interval here. Okay, so here, let's first separate out the deterministic part of the choice-specific value. Okay, so here's essentially the same Bellman equation as we had before. I put the stochastic part at the end, just signify that we don't really want that in the deterministic part. Is this part stochastic? No, it's not. It's not depending on any stochastic variables. Well, we're integrating over stochastic variables, but we're taking an expectation of a stochastic variable, which has an expectation which is non-stochastic. Okay, So really what we have is that we can write the value function in the following way as the max over all the decisions of this choice-specific value function, the deterministic part of the choice-specific value, and then the choice-specific shock. Okay. This simplifies the model greatly, and once it makes it easier also to take expectations and so on. And so here's one is this v. Well, that is just the sum of the utility function and then the discounted conditional expectation of the value function given today's states and today's decision, which is exactly what is written here. Okay. So that was the first thing we could do. And the second thing we can do is that, and this is something that is implied by the conditional independence assumption. Here I'm actually writing the model of with additivity assumption added, but it actually doesn't matter. You could have epsilon inside here, and you would still be able to do what I'm going to tell you we're going to do. Oh, sorry about that. Okay, so let's first define what we call the expected value function. The expected value function, well, that's the expectation of the value function conditional on the state and the decision. Okay, so you can already see that this is lower dimensional than the value function. Okay, because the value function here does not only depend on x, it also depends on this huge continuous state variable. Okay. Now, by taking expectations over it, we can integrate those epsilons out under the conditional independence assumption, and then the expectation conditional on the state variables and the decisions becomes only a function of those two variables, which is much lower dimensional. Say in the case of Zurcher, where choice is binary, well, you have only the one state variable mileage, and then you have these two decisions. Okay, whereas this guy here would be j plus 1 dimensional there will be j plus 1 continuous state variables. Okay. So this is easier. Okay. Now the cool thing is we can express the Bellman equation in the expected value function space rather than in the value function space, making the solution much more easy to store and easy to handle. Okay. So this is essentially what I'm just taking the definition of the expected value function, and then I'm substituting in the value function here and integrating over those variables that are stochastic and conditional on the states x and d. Okay, so obviously this becomes a function only of x and d. Okay. So here the value function is the same as before, but what I've highlighted here is that the value function is now a max of the utility plus the expected value plus the epsilon. So now you have inside here the expected value, and on the left-hand side you have this expected value. So we have now represented the Bellman equation in terms of this new Bellman operator gamma, which works on the expected value function space rather than value function space. Okay, and Russ proves that this is also a contraction mapping with a unique fixed point so that you can do successive approximations. Okay, so you get global convergence of value function iterations or successive approximations. Here the key thing is EV is lower dimensional, does not depend on epsilons. Now you can do another thing, and that's going to be useful when we, it's actually useful. It's just not written in Rust's paper. It's mostly something that we will use when we can start considering these conditional choice probabilities, because it's a conditional choice probability estimator, CCP estimators, later on, and the Hodge-Miller inversion that I talked about in the introduction for the plan of the course. Here we will express the Bellman equation in so-called integrated value function space, or some people call it the smooth value function. The difference between the expected value function and the integrated value function is that we are not integrating over the observed state variables x. So we are essentially not taking the expectation with respect to future values of x, only with future values of epsilon. So we're integrating out the epsilons. Okay, so now you got a separate Bellman equation in the integrated value function space. And again, you can write this value function here as in the same way, but now signify the dependence on the integrated value function rather than the expected value function, as we did on the previous slide. Okay, so now you clearly have a mapping from integrated value function to integrated value function, since it goes through to the value function, which is what you integrate over here. So again, we have another contraction mapping, I'll call it gamma bar, with another unique fixed point v bar, which is the integrated value function. And again, this v bar is you can find it with value function iterations in this global convergence, so you can start with any starting guess of the value functions. And then it's lower dimensional, and here it does not even depend on the decisions; it only depends on the epsilons. So I mean, if you are in the business with continuous state variables, this actually becomes an issue. If you're trying to find the smoothest and lowest dimensional object to approximate, when you want to approximate the value function, say with Chebyshev polynomials or splines or whatever approximation routine you're using. Okay, so that was kind of, you can represent the Bellman equation on a reduced state space, or the Bellman operator on a reduced state space. Now, the last thing is, and this is the benefit of the extreme value assumption, assuming that the epsilons are either extreme value type 1, we can express expectation of the maximum using the properties of that distribution, and that actually leads to closed forms expectations of maxims. This distribution has a lot of nice features, and actually I encourage you to go read about the extreme value distribution and the generalized extreme value distribution, which is max stable and has closed form expectations of maxes and closed form expectations of implied choice probabilities for models that has these types of error terms. Okay. So here, what you can see is now the integrated value function, and therefore also the expected value function ceases to compute, because the integrated value function is the expectation over those epsilons conditional on x, taking the max over all the discrete decisions. And a property of the extreme value distribution is that this gives a closed form which has this nice log sum formula. This is what it's called. So it's a log of the sum of the exponentiated values, and here scaled by lambda. Now lambda is 1 in our case. Okay, we don't have any lambda here. It's just 1, right? We normalized it to 1 because of our scaled normalization of the discrete choice model. So this is really easy to compute. I mean, of course, you need to take the exponentials of a bunch of um, of all these discrete choice-specific value functions and add them up. But this can be done very fast on a computer. Okay. The alternative is to calculate a j-dimensional integral. Okay. So we don't have to calculate any j-dimensional integrals over epsilons in order to get the integrated value function, or the Emax operator, if you will, the expected max. The same applies for the conditional choice probabilities, which we'll note P of x and D, which is closed form, a closed form logit expression. Sorry about, there's a typo here. I prefer actual this notation, but this is the same thing. Okay, so the probability of choosing choice D conditional on x. We call them conditional choice probabilities because they are choice probabilities for choosing discrete actions conditional on x. Okay, now what is that? Well, that's the expectation that the decision you're looking at is actually the optimal choice. So D is the argument that maximizes the sum of the deterministic and the stochastic part of the choice-specific value. What is that? That's just the logit formula. Again, you avoid this this integration over j-dimensional continuous states, or j-dimensional stochastic variables, and you can just put it into the logit formula. Very cool, huge benefits. Once j-dimensional numerical integration over epsilon in two cases where you need to solve the model, you need to do this repeatedly because we do this as during the course of solving the model, and also while maximizing the likelihood later on. Okay, because this is all nested inside on the maximization routine. Okay. Another thing here is P, the conditional choice probabilities, the integrated value functions, and the expected value functions. They are all smooth functions with respect to the continuous states, but also with respect to the parameters that indexes those functions, which is important when we want to estimate the model. Okay, so putting all this together. Okay, so this simplifies the DP problem under additive separability, conditional independence, and expected value. So we get conditional choice probabilities that are multinomial logistic, and I put in here the version with the expected value function because this is what Russ does in his paper. Okay, you could have a formulation where the choice-specific values inside here would depend on the integrated value function, and then you solve for that. Okay, but see here, the choice probabilities depends on the expected values. The expected values you need to solve for a fixed point on this operator here in order to obtain that. Okay, this is fortunately much simpler now because it avoids that integral over the epsilons, and so we have this closed form expectation, and it's much lower dimensional because it's not a contraction mapping on the space of functions defined by variables that are the x's, the observed state variables, and the epsilons. It does not depend on epsilon. Okay, so this is really simplifying things. Okay, so another thing I want to highlight here is from now on, I will subscript the Bellman operator with theta, okay, to signify that the Bellman equation or the Bellman operator depends on the parameters, right? Because, the parameters enter into the utility function, right? And the parameters enter into the expected value function because once you take the expectation here, well, there's also parameters here. So every time you change parameters, he's going to change the right-hand side of this equation. And since the operator depends on the parameters, well, then in turn also the solution for that equation that we're trying to solve depends on the parameters. So the fixed point, the expected value function, is an implicit function of the parameters. You change parameters, you change replacement cost, well, then the expected value of owning a bus of a given mileage will change. Very intuitive. And the resulting conditional choice probabilities are also implicit functions of theta, so we write that. Okay. Now this is important for realizing when you're trying to estimate the model. Because the model, when trying to estimate the model, we would want to vary those parameters so that the predictions for the models are in accordance with the data. What are the predictions? Well, that is the probability of replacing the engine, okay? Because you have observed data on mileage and data on replacements. Well, then you have to model that conditional probability, the binary choice model. Okay, we're not quite there yet. Okay, so it's still about how to implement the model, right? We need to also handle in some way the fact that X is a continuous state variables. And here, I think John is very explicit about that in the paper. So I'm just writing out the model here very explicitly in terms of the chosen approximation method. So Rust discretized the range of the traveled miles into 175 bins, and that's also a version of the model with 90 bins. Okay, so there's something called N, which is the number of bins that the discretized mileage can fall into. If I remember correctly, it's something like the state space goes from 0 to 450,000 miles. So if there's 90 miles bin, then each bin would correspond to an interval of 0 to 5,000 miles. Okay. And then if the state variable process is discrete, well, then also is discretized. Then also the process for the state variable. If the state variable is discrete, then also the process for the state variable is going to be discrete distribution. So we model this as a discrete Markov process, and this is can be summarized by the Markov transition matrix. I'll show you in just a second. Okay, so what he assumes here is that basically the mileage the change in mileage can only take on j different values. Okay, so say you could drive 0 to 5,000 miles, or 5 to 10,000 miles, or 10 to 15,000 miles, and then beyond that, there's zero probability that you will drive that. Okay, if that's the case, then j would be equal to 3 because of these 3 intervals. Okay. So in other words, mileage in the next period can move up at most j grid points. Okay. And he's also assuming that those probabilities of changing mileage is independent of the mileage itself. So let's see. With this discretization, well, then we can write the choice-specific expected value function for x, where this x hat are the discretized states now, in the following way. And now you're essentially summing over those j's possible transitions that we'll do instead of this, an integral over all the values of x. Okay, so we can also express this in matrix form. So now if you stack all the value functions on top of each other and all the utilities on the top of each other, you have this formula here, and essentially the Bellman operator here becomes a matrix that's conditional on the decision and multiplied by multiplied by a vector of integrated values. Okay, so that's essentially what the expected value function is going to look like. Um, yes, it's not really the integrated value, but you see the formula here, okay? And so this is just in matrix notation. So now it's really like in a finite state space, and everything can be done with simple matrix algebra in order to implement the in the Bellman operator. Let's take a look at this matrix here. Okay. Now notice it depends on D, right? This is the Markov transition matrix, which is n by n. Looks like this. Okay. What does this mean? Well, this is let's first take the transition matrix for mileage if you are not replacing the engine. So D is equal to 0. Okay. So if not replacing, then the transition matrix has this particular structure. Okay. It's like it's a band above the diagonal where there's potential positive values that's supposed to sum to 1. And then above the diagonal is just 0, and then below the diagonal it's 0. For the replacement, it looks like this. Okay. So there's a band in the couple of first rows. Let me explain why they look like this. Okay. So first of all, let's talk about why there's nothing about why is there only zeros below the diagonal in this specification of the transition density or transition probability matrix. It's because the buses are not driving backwards, right? I mean, what is this? I mean, first of all, these are here is an element that this particular element or an element in this matrix says, if you have this value of the state today, this is the probability that you end up in this state tomorrow. Okay, so imagine that the vector of state variables lying, or is like indexing of the state variables lying up here for tomorrow, and then for the day here. Okay, so this is like standard Markov transition matrices. It looks like this. Okay, so this means that if you have a below diagonal, it means that you have a high mileage, but you have a lower mileage tomorrow, right? So this would imply that the bus is driving backwards, okay? And Harold Suckers, he's like in the business. He wants to move forward. He wants to rock and roll, okay? So he's not driving his buses backwards. Okay, so what about, why is there nothing up here? Well, remember we consider a state space from 0 up to 450,000 miles. And these are monthly transitions. So if you come with a brand new bus or a bus in the first discretized value, which is as good as new, then it would be kind of peculiar if the probability of it suddenly driving 450,000 miles within a month, that's several, that's several tens of times around the world, right? 20 times around the world maybe. So within a month, it's not reasonable. So probability for that is 0. So that's why you only have these positive probabilities at just on the diagonal and above the diagonal. So on the diagonal is kind of you say and stay in the same state. Just above the diagonal, you drive a little bit more, so you move on to the next state, and the bus is aging. Now let's look at how the mileage can actually move backwards. Well, that's if you replace. If you replace the engine, well, then the mileage of the bus engine is regenerated to 0, and this is why you have all the mass in the first columns. Okay, like so here you would only have the this is the probability that you essentially drive as much is so little that you stay in the first interval, and this is as much driving as you drive if you can move up to the next interval, but starting from the first one, because you just replaced the engine in this brand new engine. So this is why it's looking like this. And notice actually, I mean, if we have 175 grid points, and say there's only a couple of intervals, like something like 4, where there's movement, then this is a really sparse matrix. In other words, there's lots of zeros. So when you implement this, make sure you take advantage of that when you code it up. Use sparse matrices or try to avoid looping through a bunch of zeros. Okay, so I think this is pretty much concluding the model. And the next thing we want to do is think about how we estimate it. Okay, so now we have an implementation of the model that we can take to the computer, because we discretize the state space. We have closed form solution for the expected values. We have expressed the Bellman equation in expected value function space that are much lower dimensional, and we have separated out the deterministic values. So this is just ready to put into the computer, and that's what you're going to do in the computer exercises. There's going to be Python code up there with notebooks and so on, and Melanie, she'll put up instructions on how to work with those. I'm going to take a little break now, and then hope you'll all be back to talk about how we actually structurally estimate the model of Harald Zurcher. That's part 2.